Hello class, Professor Smith here. Let's talk a little bit about motion diagrams, and this is a way to sort of visualize the movement of objects in the universe. And let's just think about a person running for a second. If I took a stroboscopic picture of a person running, what would it look like? Well, the first flash would go off, and they would be in that position there, and then now, a while later, I take another position, another flash, and so on. And pretend that their legs are actually moving between these shots. Okay, and now we go to the next one. All right, and so forth. Person is moving to the right like so. This is what a motion diagram looks like. It's just a snapshot of this person. And in the old days, we used to have these things called film cameras, all right? And we would open the shutter, expose the film for a very long time, and we could just take stroboscopic pictures as somebody went by. And you would get, 6 different shots of them as they went by. Now, looking at this, you already have a lot of information. Is their position, this person's in position, are they increasing or decreasing their position? If you said increasing, you might have hesitated because we didn't decide which direction was positive and which direction was negative. So we have to do that first. Let's say that this is positive, okay, to the right. And we'll just start this out as x equals 0. Okay, now just based on this picture, you already know a lot more information. Are they increasing their speed, decreasing their speed, or are they staying the same? Oh, wait. There's something very important here. There's a delta between these pictures. It's different there than it is there. Now, I could get out the measuring tape and I was trying to draw them a little closer together, but I can certainly believe that these two images are a little further apart than these two images. So the person is maybe increasing their speed. If all of the deltas were exactly the same and the spacing was exactly the same, we would say constant speed. All right? So how do we deal with motion diagrams? You don't have to draw images over and over again. That would be very cumbersome. Just make it a dot. Person at time 1, person at time 2, time 3, time 4, time 5. Okay? And then if we give you some numbers here, it's going to make good sense, okay? Let's say that this is 10 meters. We'll just call this one 0, all right? 20, 30, and 40 meters. And then each interval corresponds to 1 second, okay? So this would be 1 second in between each flash of our camera. So then based on these numbers, you would probably say the person is running 10 meters in the first second, 10 meters in the second, 10 meters in the 3, and 10 meters in the 4. So running at 10 meters per second, which maybe some of you guys could do. I know for a fact that at my advanced age I could not do that, but 10 meters per second, man, that is moving. All right, so how do we make this into a motion diagram that looks like this? So we got x versus t. Well, let's do it. Well, we have t though. Actually, we have t already. So it goes 1, 2, 3, 4, because t is the y. All right, and then we have the x measurements. So x is going to equal 10, and then 20, and then 30, and then 40. And then, of course, we're going to get a straight line that connects all of these. So in this example, this is the position versus time graph, okay? X versus t. And that actually has a lot of information right there, because now, looking at this graph, moving at constant speed, well, are they increasing their speed or decreasing their speed? It's a constant speed, right? Constant speed the whole way. If if they are moving along at constant speed, or more specifically, at constant velocity, what is their acceleration? It would be, of course, zero. Zero acceleration. So, one graph actually has a lot of information. It tells us about the position, but it also tells us about the speed as a function of time. So it's an important thing to be able to plot these things and to make sense of them. And that is motion diagrams.